Okay, so we're going to continue talking about AC motors. Um, and last time we already talked about three-phase voltage sources. Now we're going to talk about sinusoidally distributed stator windings. And then we're going to be connecting the sinusoidally distributed stator winders to the three-phase voltage source. So first of all, distributed windings. So what we see here is that we have a winding going in here that's going to come in, wrap around, and come out here. And then we're going to do one winding there. And then you're going to come up to two. And you see now we have two windings, and then three, and then four. And you see that the windings are increasing as we're moving up. And then when we're coming down the other side, then they're going to be decreasing. So you see that we have more windings vertical up here and less windings down here at this axis. And then with all these windings are all connected, and then we're going to have one current that comes into the winding, wraps around everything, and then comes out. So if we look at these as a cross section, so if we take a cross section through there, again, you can see that the size of the wire is indicative of the number of windings. So you see we have a small circles here, which means very few number of windings, large circles here that correspond to a large number of windings. So you can kind of see this is our basic equation where we basically have enough windings that we treat it as if it was a continuously varying number of windings, even though in reality it has to be discrete. So we see here that the number of windings changes with our angle as we go from 0 by the sine of the angle. So you see when we're at 90, we have the largest number of wrappings. When we're at 0, we have the least number of wrappings. The other thing is lots of times instead of having the individual numbers, we want to figure out how many total wrappings there are up to an angle. And so then this will tell us our total number of wrappings as we wrap around the whole thing, because we know how many total wire loops we have. And then we can take and break it up into this equation here, which tells us how the wrappings are related to the total number of wrappings that we're applying. Okay, so now that we have these sinusoidally varying wire windings, now we want to actually measure our magnetic field. So we're going to start up here with this equation using our Ampere's law. So with Ampere's law, you can see that my magnetic field, we can basically do a contour loop integral around certain angles. And we remember before that we basically have a small, so we have our rotor is going to be in here, and this is our stator. And so we know that most of our magnetic field is going to drop across that air gap. And so the air gap, which is this Lg, is going to define my magnetic field, because we're going to assume in this case that the permeability of our metals are infinite. So you can kind of see that our magnetic field, as we do these loops, are going to enclose a certain number of wires. So we can kind of see right here. So with this equation here, we're trying to, this part right here is our total number of wires around the loop, and then our magnetic field is only going to exist across the air gap. So our contour integral is going to be h times the two air gaps. So we're going to have, so if I have a loop that looks like, so if I have a loop that looks like this, goes through the metal, and then across like this, you can see that I'm going to have 0 magnetic field all the way around the metal, all the way across the rotor, and all of it's going to drop across this air gap and this air gap, and my magnetic field is going to be perpendicular to the air gap, because that's going to be my smallest. And then my magnetic field, you can kind of see, is going to be the total number of conductors right here, which varies with angle, divided by my two air gaps. And so what you see, if I look at this plot down here, you can kind of see when I'm at the zero angle, which would be this one here, that looks like that, you're going to see I'm going to enclose my total number of conductors, and I'm going to have my maximum magnetic field. If I draw my loop like this, that's going to be at this point right here, and you see that I have the same number coming out as going in, so my net total current is going to be 0, so I have 0 magnetic field. Then when I'm down here at this point, you see I'm grabbing the most, that's going to be a negative down here, so you can see that my magnetic field, H, and then also my magnetomotive force and my B are all related to each other, and so they're going to create this sinusoidal variation as you go around. And this is the plot of the magnitude of my fields, because we know the directions of the fields are always going to be perpendicular to my air gap. Now we're going to be applying current to these, and so you can you can kind of see that as my current goes up and down, so if this would be at one current right here, and then when I grab a different current, my total current magnitude might be higher, and so then this is going to change. So you see these would be as my current is fluctuating up and down, these amplitudes are always going to have the same distribution, but its peak value is going to increase as I go up and down. Okay, so now let's look at a snapshot in time. And so you see this is my rotor in here, and then this is my stator out here, and you can kind of see the windings going across here. And you can see that it has these little arrows, so that's going across my air gap. Obviously this air gap is exaggerated so that you can see it. But at this instant in time, you can kind of see at this angle, I get these magnetic field lines that are always perpendicular to the air gap, but the length of the line, which corresponds to its amplitude, is larger on this axis and small on that axis. What we notice from this is that every time I have an arrow, let me change this to blue. So you can kind of see that I have an arrow going up this direction. There's a other corresponding arrow that's down. When I sum these two arrows, so you see if I take this arrow plus that arrow, that the up and down parts cancel, and I'm left with a vector that goes that direction. So my vertical part cancels out. So you see that this green line right here corresponds to the sum of all of these magnetic vectors everywhere along, because every piece that has a vertical one is also going to have a vertical piece going down. So if I sum all of these together, I get this line that goes that direction. So let's go to this animation down here to show this running. Okay. So what we see here is this is showing the current that's going into these windings. And you can see as my current goes up and down, the magnitude of this magnetic field line is increasing. So right here, we're decreasing my magnetic field combination, and then we're going negative currents flowing back this other direction. If I look at the amplitude of each of these lines as we distribute around, you can kind of see it creates this sinusoidal pattern because my sinusoidal windings. And its shape stays the same. Its amplitude is going up and down. This one over here shows that this has a winding that's twice as fast. So this is called a 4-pole system, where this one over here was a 2-pole system. And in this case, we're just increase our winding percentage, or I guess our spatial frequency of the winding. It still has a sinusoidal and it still goes up and down with current, but now it varies twice as fast. So these are called sinusoidal windings connected to one current source, where this is my one current source. Okay. So now what we're going to do is we're going to create 3 of these sinusoidal windings. So this kind of shows an AC motor for the stator. And you can see that there are lots and lots of windings. So in the example that we showed before, it's going to have a low density winding here and a high density winding there. What we're going to do is now we're going to create another set of winding that's shifted by 120 degrees. So instead of having the maximum windings here, now it's going to have its maximum windings here and the zeros across here, and then I'm going to have another winding that has a maximum here and a low here and here. And so when we take these 3 shifted sinusoidal distributed windings, you get windings that look like this. So it basically looks like I got uniform windings all over because I have 3 sinusoidally varying windings all coupled together into the same stator. So let's look at that. So the way that we're going to model this is we're going to have 3 sinusoidally varying windings, and they're all going to be connected together into this Y configuration like we saw with our 3-phase power. So what we see here is we remember that the sinusoidally varying windings that had a low density here and a high density there is going to create a magnetic field that's kind of this direction. So that gets modeled by this winding. So you see this winding has a magnetic vector that's going to be going that direction. We're going to create another one that has its magnetic field line going up this direction. So that's modeled by this one. Okay, and then I have a C1 down here. So you see I have a distributed windings going around these where the magnetic axis of those windings is going to be either 0, 120 degrees, or 240, right? And 240, sometimes we call this negative 120 instead of 240. So now we have 3 sinusoidally distributed stator windings connected with different currents in this Y configuration. So what we're going to do is we are going to model these different axes with these space vectors. So the space vectors tell you the direction that your magnetomotive force and the direction that your magnetic field and magnetic flux densities are going to go. So we have one that's labeled A, and it's always going to point in the A axis, which is 0. The B is always going to point along this axis right here, which is my 120 degrees. And then I'm going to have a C that's going to vary along this axis, which is my minus 120 degrees. And so you see that these vectors are always going to stay on their corresponding lines, but they're going to change in amplitude. So as my currents change, the lengths of these lines are going to change. And then what you can see is we can take these individual magnetic fields. Since it's linear, those magnetic fields are all going to add together. So then I'm going to take my A plus my B plus my C to get my total magnetic field line. So this A is produced by this winding, and that's this vector FA right here. And then we're going to have this winding right here with a current that's producing this FB right here. and then we're going to have this axis is this FC, so I sum those three together, and then this is my total magnetic field vector built up by the magnetic field produced by the three sinusoidally varying windings. Okay, so now let's look at an example. Okay, so we have a sinusoidally distributed stator winding. So this has 3 windings. The total number of turns for each winding is ns over 2, which is 50. And at some instant in time, we're going to have the current in my A axis right here is going to be 8 amps. The current in the B is going to be minus 9.2, and the current in the C is minus 1.2. So we okay, sorry, I made a change. So the current in A is 8, the current in B is minus 9.2, the current in C is positive 1.2, such that when I sum these three together, they have to equal 0 because I have the Kirchhoff's current law right here. So these three currents, since they're in a Y configuration, have to sum to 0. And this instant in time, we get this variation. We have a air gap of 1.5 millimeters. We're saying that the permittivity in the metal, which is in the rotor and in the stator, are both going to be infinite, such that all of our magnetic field is going to drop across the air gap. And we're trying to find our magnetic flux density. Okay. So what we're going to have to do is we're going to start by finding our magnetomotive force, which is labeled as F. And the magnetomotive force is going to be the number of windings for that times the current that's going into my A winding times the directional or my state vector for my A winding plus the current in the B times the B vector times the current in the C times the C vector. So we're basically just kind of summing up the 3 windings and the magnetomotive force produced by each winding. Okay, so here is my ns over 2, and now we're going to take and put okay, so I corrected the error. So there was this IA has 8 amps and it was showing 10 amps over here. So you see all of a sudden all the numbers changed. So I went and corrected the numbers. So let's go to MATLAB and show how we're doing all of this. So let's start with our vectors. So we have our A vector, which is 1, 0. So it's pointing in the x hat direction. We have our B vector, which has the cosine of 120 and the sine of 120. And then we have our C vector, which is the minus 120 for the x and the y. So then what we're going to do is we want to do, you see we're going to do 8 amps times A. So that's going to be 8. And then we're going to have minus 9.2 times my B. And then we're going to have plus 1.2 times my C. So you see these numbers are right here. This is my 8 times A. This number right here is my minus 9.2 times the B, which is this part here. And then this part here is my 1.2 times my C. And then when we get the whole thing together, we're going to go 50, which is my ns over 2, times, then we're going to go 8 times A minus 9.2 times B plus 1.2 times C. And you see that number right there, that is equal to my F. Okay, so that's this F right here, which we plug it all down. That's this F right here. So now we want to convert from F to my magnetic flux density B. So I'm going to take F divided by my air gap distance times my permittivity of the air gap, which is going to be equal to mu naught. So then my B is going to be equal to F divided by 1.5 milli times 4 times pi times 1 e to the minus 7, which is the permeability of free space, or the permeability of the air. And so then I get this number right here, which is right here. That's my magnetic flux density produced by these currents with this air gap and this number of total turns for each winding. Okay, so now we want to look at the vector magnetic flux density. So what we're going to do is we're going to apply a three-phase voltage to the sinusoidally varying windings. So the A phase current is going to go into the A winding, the B current is going to go into the B winding, and the C current is going to go into the C winding. So we're going to start with this. This is what we had before. My magnetic flux density is my magnetomotive force divided by my air gap times my permeability of the air gap. Okay, so then we're going to take in and we're going to plug in for F is going to be the current in the winding times the spatial variation of the winding, plus the current in the B winding times the spatial variation of the B, and so on with the C. Now we're applying a voltage. So the voltage is this three-phase voltage. So to get the current, we found when we did the three-phase stuff that the current is going to be equal. And then, so this is a line to neutral voltage divided by the impedance of the winding. And then we're going to do the same thing for the B and the same thing for the C. So now what we're going to do is we are going to couple in that my A is going to be some voltage times the cosine of omega t. My B is going to be the same voltage times the cosine of omega t minus 120, and then my VC is equal to the cosine plus 120. The A vector is my x hat. My B vector is this one. So this is my 120 degree spatial winding axis. Then my C is going to be this. So you see I'm taking my A voltage times my A spatial vector, my B voltage times my B spatial vector, and my C voltage times my C spatial vector. Now we have to do a bunch of algebra in order to simplify this down. So the first thing that we're going to do is we're going to take this cosine and this cosine and convert them into, using a trig identity, into a variable here. So you can kind of see that we're converting this into numbers. So we have this 1/2 and the square root 3 over 2, which is our 120 degrees cosine and our 120 degree sine. So then, and we do the same thing for the plus 120 degrees. And you see the main difference is that I get a sign change on my sine part. So now I'm going to take these variables here and plug them in for this and for that, and then we're going to combine together all of our x hats, all of our y hats together. Okay, so we start by plugging in. Here is our base magnetic flux, which is just all of this stuff combined together. And then we're going to have the cosine omega t times x hat. This is my cosine of omega t minus 120 times my A. So this is my VA, sorry, this is my VB, this is my B vector. This is my VC, this is my C vector. And then we're just basically going to multiply all of this out and collect together all the x hat and the y hat terms. So we multiply all these out, and these are all my x hat terms. These are all of my y hat terms. What we see here is in the x hat piece, I have this piece and this piece, which are both negatives of each other. So these two are going to cancel out. For my y hat, you see that this piece and this piece are the same. So these two are going to cancel out. And then I'm left with a bunch of cosines here. So I get 1 plus a fourth plus a fourth. So that's 1.5. So that's this 3/2. And then down here, I get a 3/4 and a 3/4. So that's 1.5 here. So when I combine all of this together, I end up getting an x hat term that depends on the cosine and a y hat term that depends on the sine. So we're basically creating something where the axis changes with the omega t. So I'm basically at one point in time, I'm going to have like an x this direction and a y that direction. And you see it's going to have an axis here. As my omega t changes, the amplitude of my B stays the same, and it varies with omega t. So we're basically creating a magnetic flux vector that rotates with angle. So let's go look at this with an animation. Okay, so here are our three phases. So you can kind of see in the A phase, like we showed before, its magnetic flux is always staying horizontal. The B phase is always going up and down along this 120 axis, and the C phase is going up and down on this minus 120 degree axis. And the amplitude of the lines is a function of how much current is going through the winding. So if I look at this plot right here in the middle, you can see I have the three-phase windings. So the currents are going to go up and down with this 120 degree phase shift. When I take the blue line plus the green line, the red plus the green plus the blue, that's what's showing here. So you can kind of see as my red goes down and up, its length gets longer, the green one's changing length, and the blue one's changing length. We take these three and add them together to get my total magnetic flux. What we see is that the total magnetic flux has the same amplitude, and it's just rotating around. And that's kind of shown in this one right over here on the far left, that the magnetic flux is almost like it's just rotating around. So what we've created is we've created a rotating magnet, right? Where the length of the magnet stays exactly the same, but we're rotating it using the phase of our voltage, not a physical change. So we get a spatially varying magnetic field that's all changed electrically. And that's the power of this three-phase power plus the sinusoidal windings. You can also see it all put onto the same thing. So you can kind of see what this one is showing, what it really looks like, where we can kind of see that the windings are all kind of stacked around the same stator. And we still get these three that add together, and then this outside one makes it seem like that's what we're producing is a rotating winding. But we get this rotating winding created electrically. And that's the power of AC motors. That's the key to creating these AC motors.